Welcome. What we discussed in the last class is we derived the equation of elastic curve, which is essentially the mathematical representation of beam undergoing deformation, linear elastic beam undergoing deformation, and the deformation is small. That was the assumption of that model. Now, we need to once the mathematical model is derived, the next step is to solve those equations, right? What we are going to do today is we are going to show you one way of solving those equations, that is direct integration method. Now, before we do that, let me show you something. Okay, consider suppose this is a beam, this is a piece of paper. Consider this is a beam, this is the length of the beam, and this is the cross section of the beam. This is the cross section of the beam. The thickness is very small. Now, let us what I'll do is I put that beam on a support and apply some load on it. Let's see what happens to that. Okay. Suppose these are support, these are two support, right? Now, these are two support. Okay. Now, put this beam on this. This is my mobile, which is not very light. When I keep my mobile here, so essentially the whatever self weight of the mobile, that will be exerted on the beam as a uniformly distributed load. So, I keep it and it fell down, right. Next, what I do is take the same beam, but now it is folded like this. It is folded like this. Okay. But same length, it is same length, same dimension, but only thing is it is folded like this. It is folded like this. Keep it here. Let's keep it here. Okay. And then, yes, then I keep my mobile on this. You see, it is perfectly stable, no problem at all. Now, the same beam, same piece of paper, when it is used as it is, then we found it was not stable. But now, when it is folded, we found it is now enough to take care of the load exerted by my mobile. Okay. Now, I am not going to tell you the reason behind this. By the end of this lecture, you should be able to explain this phenomena. Okay. Now, let us take one example. This is the example. Okay. Example that just now we showed, that is a simply supported beam. This was the simply supported beam, this length, and it is subjected to uniformly distributed load Q from it is from the self weight of the mobile, and these are two supports. Okay. What we need to find out here is we need to determine what is the deflection of the beam at any distance x from support A, using equation of elastic curve. The equation what we have is d2 minus m by ei, where m is the since m is a function of x, better write mx as a function of x. Okay. So, curvature is equal to moment at a distance x divided by Young's modulus and divided by second moment of area, right. Okay. So, first determine the support reaction, and we have seen this problem many times in this course. So, if we apply if we draw the free body diagram of the entire structure and apply the equilibrium condition on this, then the support reactions will be Ax, that becomes 0, and Ay is equal to By is equal to q into L by 2. We know how to determine this. So, I am not going to do it again here. Take a section here, say 1 1, which is at a distance x from the support, and if we draw the free body diagram of this, what we have, this is a y, ax is equal to 0. So, not writing explicitly, this is q, this distance is x, and then this is moment x, and this is shear force Vx. This is the free body diagram of this part. Okay. Now, if we take moment about this point, then what, summation of mx is equal to 0, and this gives this gives us ay into x, ay is clockwise, and then minus qx, which is the total load, into x by 2, that is equal to 0. So, and this becomes ay is equal to ql by 2 plus minus mx. Mx is clockwise, anti-clockwise, that is why it is minus. So, this gives us mx is equal to ql by 2x minus qx square by 2. So, that is how the moment changes with x. We also have derived this by in the first week when we reviewed bending moment and shear force diagram. So, this is mx. Okay. Now, we assume in this problem that Young's modulus is constant, and the cross section of the beam is uniform across the length. So, E and I both are constant. So, only variable in this, only parameter which are only thing which is function of x is the moment. Okay. Now, what we will do is, now this differential equation we will directly integrate. So, substitute, if we substitute mx here, what we have is this. So, d2y dx2 is equal to, or you can write ei here, minus mx becomes minus ql by 2x plus qx square by 2. Okay. So, if we integrate it, then what we have is ey dy dx is equal to integration of entire part, ql, q are all constant. So, this becomes minus ql by 2 x square by 2 plus q by 2 into x cube by 3, and then plus a constant C1, which is constant integration constant. Okay. Now, again if we differentiate ei first time, and the second time if we differentiate, then y is a function of x. I am not writing explicitly in x in bracket. So, this becomes minus ql by 4 x cube by 3 plus q by 6 to x to the power 4 by 4 plus C1x plus C2. Again C2 are the another constant, C1x into C2. Okay. Or let us write here C1x plus C2. Okay. Now, this is one constant and this is another constant. How to determine this constant? We need to apply boundary conditions to determine this constant. Okay. Now, here one point, please note, this equation alone, this when we, if you remember, Again, in the first week we discussed when we were talking about the physical process, then idealization, and the mathematical model for the idealization. I mentioned there that when I say the mathematical model, it means the equation along with the conditions that the equation that the variable should satisfy. For instance, in this is the equation true for any problem, any beam, transversely rotated beam, this equation is true. Now, when you solve this equation, this is a very general equation, when you solve, but for this particular problem, in order to get the unique solution, we need to give some constraint. The constraint is these boundary conditions, and these boundary conditions will help us to determine these constants C1 and C2. Okay. Otherwise, if we do not have these boundary conditions, then we cannot determine the constants C1 and C2, so we cannot have a unique solution, right? Now, let's see what are the boundary conditions we have. This point is pin support, and this is roller support. So, slope is not 0 here. Here also slope is not 0. We have y is equal to 0 at this point, and y is equal to 0 at B. So, boundary conditions we have boundary condition for this problem, we have y at 0 is equal to 0 and y at L is equal to 0. So, what we will do is we will apply this boundary condition in this equation to determine these constants. Okay, let us do that. Okay. Now, the equation was EI y Okay. Now, first boundary condition it y is equal to 0, y is equal to 0, y 0, y is equal to y at x is equal to 0 is equal to 0. If we substitute x is equal to 0 here, then what we get is C2 is equal to 0 directly. Okay. Now, another boundary condition is at x is equal to L, y is equal to y of at L is equal to 0, means x is equal to L, y is equal to 0. If we substitute this, then this gives us right hand side, the left hand side becomes 0, that is equal to minus QL by 12 L cube plus Q by 24 L to the power 4 plus C1 into L is equal to 0. Okay. And then only unknown is C1 here. If you calculate C1, then C1 will get Q L to the power L cube by 24. C1 is equal to this. Okay. Now, in this equation C2 is equal to 0 and C1 is equal to this. Now, substitute C1 in this equation. If we do that, what we get is as this. If we substitute that, then we will get y is equal to, let us take 1 by, let us take E by EI here. So, what we get is 1 by EI into Q L cube by 24 x, this is this term, and then minus Q L by 12 x cube, this is this term, and then plus Q by 24 x to the power 4. I am written in the as the increasing order of x. Okay. Now, it can be slightly more modified. This becomes, if we take 24 1 by q is common, 24 EI, it gives me L cube x minus 2 L x cube plus x to the power 4. So, this is y is equal to. So, this is the expression of y as a function of x. Okay. So, if we look at this beam, this beam will deflect like this. This beam deflect like this, and that deflection, the deflection at any point, if this is y, that y can be obtained by this expression. Okay. Now, is it consistent with this at x is equal to 0? Yes, y is equal to 0. If you substitute at x is equal to L, then also y is equal to 0. Now, since the beam is symmetric, let us find out what is, at what point the deflection is maximum. You can do y is equal to, expression of y is equal to this. So, for maximum, when deflection is maximum, then dy dx has to be 0, dy dx has to be 0, and at that, when you substitute dy dx is equal to 0, it gives you an expression, and you get what is the value of x where y is maximum. Okay, but at least for this problem, since it is symmetric, we can say that y is maximum at the at x is equal to L by 2. Now, if we substitute x is equal to L by 2, then what we get is y is equal to, for this problem, y max is equal to 5 q L to the power 4 by 384 EI. This is a very standard result. So, you can it is better to remember these expressions. Okay. Now, this is these results, it is very handy if you remember these results. Okay. So, what it says that this is the maximum deflection at the for this beam, for the simply supported beam subject to TUDL, and the deflection is maximum at the at x is equal to L by 2. Now, let us see what are the expressions we have, what are the parameters which can influence the maximum deflection. Okay, the first parameter is this is the problem. The first parameter is Q, which is the self weight of this, which is the load acting on this beam. So, by intuition we can say that if Q is more, then deflection will be more, and this is consistent with this expression, that if Q is more, deflection is more. Now, here another point to be noted is, you see, we as I mentioned, we assume the material is elastic. The structure behaves in such a way that the Hooke's law is applicable. So, deformation is linearly dependent on the load, and if you see in this expression, again this is evident that if this is a deflection which is linearly depends on the load. Okay. Now, then it changes with L. If we instead of if you have a shorter length L, the deflection will be less. If you have length is more, then deflection will be more. By intuition, we can say that the deflection should increase with increase in length, but how much, at what proportion, at what order it will increase, that gives you this expression. It will increase the fourth order. Okay. So, then this is the Young's modulus. So, Young's modulus is more, means the structure is more stiff, and if the beam is more stiff, so naturally the deflection will be less. So, which is also evident here, that the deflection inversely proportional to the Young's modulus. So, stiffness, more stiffer beam, less the deflection. Then it is second moment of area. It says that it is also inversely proportional to second moment of area. So, if second moment of area is more, deflection is less. Okay. Now again I go back to the the example that I showed. When the beam was like this, what happens? The length is this. In both the cases, you see, when this is the first beam and this is the second beam. This is the second beam. In both the cases, length is same. So in both the cases, the applied load on this beam was same. The both are made of same material, same paper, so Young's modulus is also same. But what was not same in both cases was the second moment of area. Now you see, I believe you know how to compute second moment of area. For this case, when your beam was, the cross section was this, second moment of area was very less. But when you make a cross section like this, then your second moment of area becomes much more as compared to this. As the second moment of area increases, then naturally your deflection is less, and therefore this can carry whatever load we applied on the structure. Okay. Now this observation we will see all the problems that we follow, we will find out the same observation. Now suppose we have a problem like this. So you have a problem, it is simply supported beam and then it is subjected to uniformly distributed load, and then on top of this load you have some concentrated load like this, P1, P2, something like this. Okay. Now as the effect of these loads are individually, if you see, since the deflection is linearly proportional to the load, what we can do is we can decompose, we can divide this problem into three sub problems are as follows. This can be taken as a beam which is subjected to only uniformly distributed load Q, and then plus a beam which is subjected to P1 and then another plus subjected to another load P2. So get the deflection of this beam, this delta 1, this is delta 2 and this is delta 3 at any section, then total delta will be delta 1 plus delta 2 plus delta 3. This is the total deflection. Okay. And it is not only for deflection, you can apply the same thing for internal forces as well. For instance, for this beam, if you have to compute the moment at any particular section, you can decompose into three parts, get the moment here, or shear force, and add them together to get the final moment and shear force for this member. This is called principle of superposition, means we are superposing different problems and get the solution of the actual problem. Okay. So this principle of superposition is applicable here, because we are our one of the major assumption is the linear behavior. Okay. If the behavior is not linear, then it may not be applicable. Just to give you one how this approach is, how divide into smaller part is it makes your life easier. Let's give you one example quickly. Suppose I have to this is the problem, this is Ly2, this is Ly2. Okay, A, B, C, and this is Q. So it is simply supported beam which is subjected to uniformly distributed load over half length, and then another half length BC and has no load on it. Now we need to find out what is the deflection of the beam. Now if you remember when we discussed bending moment and shear force diagram, for this kind of problem we had two expressions for this problem. We had two expressions for bending moment. One expression which is applicable, which is true for when x between A to B, and another expression when x between B to C. But these two expressions should have common value at B. Okay. Now, so now when you solve this equation, d2y dx2 is equal to minus m by ei. Now m is different for the expression for m is different for this part, and expression for m is different for this part. What you need to do is, now we need to apply this expression here, apply this expression here with expression of moment at this point, and again apply this equation on part BC with the expression of moment you can have for BC. Okay. Now when you apply for this part, this will give you two constants, because it is a second order equation. This will give you two constants as C1 and C2. Okay, like in a simply supported beam, when we integrated it, we had two constant, and those constant we could determine from the boundary conditions. Okay, now when we apply this equation over AB, this will give us two constant, and we need to determine these two constant. Now again, when we apply this equation over BC, that will also give us two constants. So they say this is C3 and C4. Now we have in the problem total 4 constants, and then let's see how many boundary conditions we have. Very straightforward boundary condition is, at this point deflection is 0, at this point your deflection is 0. So y at x is equal to 0, y0 is equal to 0, and yl is equal to 0. Okay. Now these are two boundary conditions, but we have 4 constants. We need 4 constraints, 4 equations to determine these 4 constants. Now what are the other two boundary conditions? You see, when we write this equation, that is a differential equation where we have a second derivative of y is equal to m by ei, it is implicitly assumed that y should be y is differentiable up to second order. If y is not differentiable, then what happens, this equation itself is not valid. So that we can use as criteria to get another 2 equations. You see, in this beam, maybe their bending moment expressions are different for AB and BC, but if we look at the deflected shape, the deflected shape should be continuous at B. Okay, deflection should be such that there is no jump in y at B. So y should be continuous at B. Because if y has a jump at B, suppose if your deflected shape cannot be like this. Deflected shape cannot be like this, because if your deflected shape is like this, then y has a jump in this. If y has a jump, then this equation itself is not valid. Okay, so your deflected shape will be continuously smooth deflection, isn't it? So at x is equal to B, so one condition is that at y is equal to B, that y at L by 2, your deflection computed from this part and deflection computed from this part should be same. Means delta at B computed from AB should be equal to delta at B computed from part BC. Okay. So this will give you one more equation, and what another equation? Similarly, not only the deflection, slope also has to be continuous to have this equation valid. So dy dx at L by 2, it is then, so this is slope, say y dash at B computed from AB should be equal to y dash at B computed from part BC. So these are 4 equations, and you apply those 4 equations to get the 4 unknown. For instance, if you have a problem like this, the similar concept can be used. These are very standard problems. If you take any book, then these problems, the solutions of these problems are given. What I am telling you the concept behind the solution. So say in this problem, you have an expression for bending moment for this part, and you have another expression for bending moment for this part. This part we have 2 constant, this part we have a 2 constant, boundary condition y is equal to 0 here, y is equal to 0 here, 2 boundary conditions. We need 2 more constant, y is equal to y computed from this part, y is continuous at this point and slope is continuous at this point, another 2 constants, and all these 4 constants will give you 4 boundary conditions. Now again, now if we now just one before we close, one small you can think of a puzzle also. Suppose consider this problem. Once again, this is L by 2, this is L by 2, this is Q A B. Now if this is C, if the problem is compute delta C, okay, what we need to do is how to compute delta C. Just now we discussed the procedure. We have two parts, one part here, another part here, 4 boundary conditions, 4 constant, determine those 4 constant. We can get the solution of this part very quickly, playing a trick. You see, this is, can we say that this problem and this problem, see there is no horizontal force, so Ax is anyway 0. So can we say that this problem and this problem are same? A, B, C. This problem and this problem same? They are same, because it is just one is mirror image of another. Okay, there is, okay. So these two problems are same. Great. Now if these two problems are same, then delta C here and delta C here, they should be same, isn't it? Suppose it is delta C 1, delta C 2. So we can say that delta C 1 is equal to delta C 2. Okay. If we add these two problems, so these are same. If we add these two problems, then what happens? Then for individually for this problem it is delta C 1, individually for this problem it is delta C 2. If we add these two problems using principal superposition, then what problem we have? From this problem A, C, B, and then from this problem it is L by 2, L by 2. So it is a beam uniformly supported, it is a simply supported beam subjected to uniformly distributed load, right. So this plus this is equal to this. Suppose this deflection is delta C. Okay. So we can write delta C is equal to delta C1 plus delta C2. Again delta C1 and delta C2 are same. So we can write delta C is equal to 2 delta C1 and delta C1 is equal to delta C by 2, isn't it? For this problem just now we computed delta C is equal to 5 Q L to the power 4 by 384 EI. So if you substitute here you get the delta C1. Okay. So what point I wanted to make here, you have a problem and don't jump onto to the problem and try to solve it. You see the problem and then plan your approach of solving the problem. Okay. Solution is, as far as concept behind the solution is very straightforward. The solution has itself is a very minor role, at least in this case, but what is important is the understanding the problem and how and formulation of the problem. There are many cases where the same problem, if you formulate in a different way, then your solution becomes easier. Okay, so that please you keep in your mind when you do some exercise. Okay, that's all for today. What you do, please go through any book and do some exercise, and next class what you do is, next class we will see another method called moment area method for determining deflection of statically determinate beams. But again, even if in moment area method the underlying principle, the premise of that method is again same equation of elastic line. Okay, thank you.